Learning target 28 again involves the work-kinetic energy theorem. We're going to be using this to figure out the change in an object's kinetic energy or speed if we have certain forces being applied to it. So rather than knowing about the work from those forces, we're just going to know the value for those forces. Or we could go the other direction and figure out the force that's required to cause a certain change in kinetic energy. One that they frequently do is to cause an object to stop, and that's what we're going to be looking at here. So we've got a 1,200 kilogram car, and we'll say it's traveling at 25 meters per second initially, and the driver sees something out ahead 65 meters and slams on the brakes and is sliding after this point. So we have a value for mu for the coefficient of that'd be kinetic friction, so mu k is 0.30. The final velocity needs to be 0, and the question here is, does the car stop in time? So we could solve this one using the kinematics equations once we use the Newton's second law to figure out the acceleration, but we're not going to do it that way. Instead, we're going to use the work-kinetic energy theorem. So we're going to determine the force that's required in order to bring an object to rest in 65 meters, and then figure out if we have a big enough force to do that. So we know that the net work on this object has to equal the change in kinetic energy. The work is just going to be done by the friction here. So work from friction has to equal, if this thing's going to stop in time, the change in kinetic energy, which is 1/2 mv squared minus 1/2 mv naught squared. And in our next line, that final velocity is going to be 0. So this just drops out, and we've got negative 1/2. The mass of the car was 1,200 kilograms. And our starting velocity was 25 meters per second. So the work from friction that has to take place will be equal to, oops, I forgot to calculate this one. Looks like negative 375,000 joules. Okay, so that's the amount to stop the car. Now let's look at how much work friction can do over that period. So we've got an unknown force of friction, but we have the value for mu. So that's our first step, is finding the force of friction, and that's going to be equal to mu times the normal force. In this case, since we have our object at rest in the vertical direction, we know that the vertical forces have to balance each other out. So we'd have a downward force of gravity or weight, and then an upward force of the normal force from the road. So in this case, normal force is just going to be equal to mass times the acceleration of gravity. So here our frictional force is going to be equal to, I'll just go ahead and add now that it's going to be to the left, so that'll be a negative. Our coefficient of friction was 0.30. The mass is 1,200 kilograms, and we've got 9.8 meters per second squared for acceleration of gravity. So the force of friction in this case then is going to be that 0.3 times the 1,200 times the 9.8, and we get 3,528 newtons. So now the work that force would do is going to be equal just to the magnitude for that force times the distance, the r vector, times the cosine of the angle. So work from friction, is going to equal 3528 newtons times 65 meters times the cosine of the angle, which here we've got our r vector going to the right and friction going to the left, so that'll be just 180 degrees. The cosine of that is -1. And I guess I really didn't need that negative sign up there earlier, because it comes out in the cosine of the angle. So now we take that force that we calculated times 65, and we get our frictional force is equal to 229,320 joules, and that's negative. And that value is less than the work that we calculated over here that friction would have to do in order to stop that car. It only does this amount. So that car is still moving when it's traveled 65 meters. So the answer here is that no, the car does not stop in time.